Morning. I'm Brad Wilson on the ASP.NET team. I'm joined by
Levi Broderick
and Damien Edwards.
We're here to talk about async and ASP.NET. So just a reminder, if you have questions during the presentation today, you can tweet them with hashtag #CH9Live. Hashtag #CH9Live. You can also participate in the Jabber chat room, ASPConf CH9. We have our helpers, including John, who you just met, sitting in the chat room and watching the Twitter feed for questions. So what we want to start out with today is a brief history of asynchronous programming in .NET. .NET 1.0, nothing. If you were using this about 10 years ago, one of the first requests people said when they got .NET was, what about asynchronous programming? So 1.1 added this new feature called APM. And the idea behind APM is that you have a pair of methods for every asynchronous operation. You have a method that begins the operation, usually begins with the word begin, and a method that ends the operation, usually begins with the word end. And the begin method will return you an object that implements the interface iAsyncResult. iAsyncResult can be used to query and find out what the status of the request is. And that's important because when you get an iAsyncResult, you need to make sure that the request is completed before you call the end method. And then when you want to get the actual result of the asynchronous operation, you call the end method, you pass in the async result, and you get back the result that happened from the asynchronous operation. So this is some example code of what it looks like. His completed property on iAsyncResult is how you check to figure out if the operation is done. Moving on to .NET 2.0. 2.0 added an event-oriented pattern for async. And the way this worked was you would call a method that usually ended with the word async. And this method started operations in the background for you, just like the 1.1 version. But what's different here is that you would subscribe to an event to find out when the operation was complete. So you didn't get back an iAsync result or anything like that. So oftentimes, unless the API gave you an opportunity to query its status, you really didn't know what was going on until the event got called. You really don't know when that event would be called. Just as importantly, because the event is asynchronous itself, it's probably going to be called in a different thread than the thread you started the request on. Why is this important? Well, a lot of things in programming.NET have thread affinity. So if you do anything with user interfaces like Windows Forms or WPF, there's thread affinity for the UI. You're not allowed to manipulate the UI unless you're on the UI thread. Similarly, in ASP.NET, there's thread affinity for the request and response. So you don't want to write to the response or query the request without being on the right thread. So then in .NET 4, the task parallel library was introduced. And what this did was, you'll notice that this pattern looks a lot like the version from 1.1 in that you call the method to start the operation, you get back something. But what's different is there's no end method to call to get the result. The object you get back is a task or a task of T. And importantly, not only can you get status about the actual operation in flight, the result itself is encapsulated in that task of T. What's nice about this pattern, better than 1.1, is that you can use it to collapse multiple operations together. Because the task of T is self-contained, you can take a task of T and then write a continuation on it, like I've done here with continue with. Do something with the result of that task, and then the result of that continuation is another task, perhaps even of a new data type. So here I turned an int into an int that I multiplied by 2, but I could even transform a data type, like so I could turn the int into a string, or turn the int into some rich class. So that's one of the nice things about the TPL in 4.0. 4.5 took the TPL and added async and await keywords that allow you to write code that looks like it's synchronous, right? It rewrites top down in a sequential manner like you're used to writing, but it's not actually synchronous. The await keyword lets you sort of interrupt the synchronous nature of the method while still writing sequential code. And we'll see some examples of this today because this is sort of the primary way that we encourage people now to write async code in .NET. And what's nice about this is, you remember the thread issue of what thread do I show up on? Async and await actually already take care of getting you on the correct thread, and they also do it in a way that's extremely high performance. It'd be very difficult for you to do it, or very time-consuming for you to do that on your own. So why not let the compiler do all the work? And then lastly, iObservable of T was introduced in .NET 4. And you can think of this as similar to iEnumerable of T in that it returns a bunch of data, But instead of being a pull model where you ask the IEnumerable of t for more data, it's a push model where it calls you back and says, I have new data for you. And when you want to observe something, you have an observer, and you can get one of three events. Either I got new data, or I got an error, or I'm done. So, threading in ASP.NET. Levi.
So I'm going to discuss what happens when a request comes into the web server and how the web server uses threads to process that request. So as a very first step, the request is actually received by http.sys and then placed into the IIS request queue. When IIS has resources to process this request, it's going to create a work item corresponding to stage 1 of request processing. This work item is going to go into the IIS native thread pool. In this thread pool, each dot represents a work item, so this one might be stage 2 of some other request, some other dot might be stage 6 of some other request, and so on. Eventually, an IIS native thread is going to start dequeuing work items from the thread pool, and one of the threads is eventually going to hit the work item that we just put in there, the work item corresponding to this request. Now, IIS native threads are highly optimized for running native code, as you might imagine, but IIS is also very, very good at particular scenarios, such as serving static files, .txt files. And in fact, the default behavior of the web server is such that if you're accessing a static file, ASP.NET's not even hit most of the time. So because ASP.NET's not hit, the request is very, very fast. It stays in IIS the whole time. Now imagine instead that you're actually accessing an ASPX page. So IIS says, hey, I need to hand this request off to ASP.NET. What it'll do is it'll give it to us, and we'll add the request to our own ASP.NET request queue. This frees up the original IIS native thread so that it's able to dequeue a new work item from the IIS native thread pool. Meanwhile, ASP.NET will decide at some point, hey, I have resources to process this request that was just passed to me, and it will do the same thing that IIS did. It will create a work item corresponding to your manage modules begin request method, or your authenticate event, or page.process request, or something along those lines. That work item gets dispatched to the CLR thread pool. Now, in this thread pool, each of these dots, again, might be other requests that require managed code to run. Maybe one of these dots is a timer callback. Maybe one of them is a call to threadpool.queueUser work item. Because this is a thread pool, there are managed threads that continually dequeue work from this, and one of those threads will eventually start processing application code, the work item that we just passed to that. Now, something to keep in mind is, while a thread is processing a work item, that thread is unavailable to process any other work items that are in the thread pool. This could potentially lead to a condition known as thread starvation, where the thread pool continually fills up with work items, but there aren't enough threads to process them because they're all busy handling other work items. The CLR is actually pretty good at detecting this. It continually monitors the ratio of work items to threads that are processing them. And if there are too many work items, if there's a backlog of work items, it will actually inject a new thread to start processing items from the thread pool. Now, the rate of injection is pretty small, around 500 milliseconds per new thread injected. If the thread pool continually builds up a backlog, your application can start suffering in terms of response times, and your users are going to start seeing spinning hourglasses rather than the actual content that you intended to serve them. Now, in order to make sure that each thread is making forward progress, ASP.NET exposes a lot of asynchronous points so that you can return a thread back to the thread pool so that the thread can start processing other work items that do have work available. I'm not going to go over this right now. This slide's just for reference, but you're going to see most of these in the upcoming demos. Now, I want to hit on one more thing that Brad said, and that's in ASP.NET, we have a bunch of per request types, HTTP context, request, response, and so forth. And these types are thread affinitive. They're sensitive to the particular thread that's calling them. If you need to access something like HTTP context, you're free to do it from the request thread, which is the thread that had originally started processing application code. For example, page.processRequest is running on the request thread. But if you're on just some arbitrary background thread and you need to access them, we recommend that you do it via a call to synchronization context.post if you're on 4.0 or below, or if you're on 4.5, just use the async and await keywords, which will do the right thing automatically for you. And you'll actually see these demoed here in a few minutes.
Okay, so now that we have a good understanding of how async in .NET has sort of evolved over the numerous versions, and then how ASP.NET actually deals with the requests and moving from one thread to another, let's have a look at the concrete scenarios when you'd actually want to use these async points that Levi just alluded to in ASP.NET. So there's really three concrete scenarios where you should be thinking about perhaps using asynchrony in your ASP.NET application. The first one, the most popular one that people associate with this, is I/O. So this is any time that your code is calling out outside the realm of your app domain and essentially making a network call, hitting a database, or even just hitting the file system, whether that be local or on another box. The second one is to do with parallelism. So if I have to have a single request perform multiple operations before I can return a response to the user, sometimes I may want those things to happen in parallel so that that single request can return quicker. And we'll talk a little bit more about that in a moment. The third one is long-running event-driven. So this is where a request is going to take longer than usual because it's waiting for some other arbitrary event to take place, or related event. A great example of that is something like Signaler. So the first one, I/O. As I mentioned, this really covers the situations where your code has to call out to the I/O subsystem of the server in order to get information from some other location. Really concrete examples of this may be a web service call that you make from a code behind or an MVC controller, maybe scraping HTML off an external website and then processing that before you return a response. Obviously a database call, and lastly file reading and writing, whether it's on the local server or doing it over a network call, maybe to a network share. I/O is really highly optimized in Windows, and so if you are doing these types of operations, there are APIs available to you in .NET to do these in an asynchronous fashion and then return the correct construct back to ASP.NET so that it can do all the great things that Levi was just talking about. And as I said, doing so lets ASP.NET reclaim that thread so that it can serve other requests and do other work while that async I/O operation is in progress. So if you are doing any type of I/O in your application, which almost all applications do, this is something that you might want to look at. The second one I mentioned was parallelism. So this is where we're going to call multiple APIs, which may be asynchronous or synchronous, in parallel so that I can decrease a particular request's response time. Now, the thing you have to be careful here is that you might actually end up using more resources if doing this. Say you have a dashboard and you have to aggregate information from 20 different locations in order to show information on this dashboard. If you want to call out to 10 different APIs as part of those 20 and they're synchronous, the only way you're going to do those in parallel is to start up new threads. There's really nothing else you can do. And there are multiple ways to start new threads in .NET, and we won't go into those now. But the advantage of doing this, obviously, is that if you're going to perform these 10 things at the same time, rather than doing them sequentially, the overall request time can be reduced. Now, the caveat of this is that you're going to hurt concurrency, because as Levi pointed out, if I'm going to start firing up my own threads from the thread pool and the CLR, I'm taking away resources from ASP.NET that it could otherwise be using to handle other requests. So the use cases for this are very, very small. Really, it's useful for when you have a limited use scenario, a limited user scenario. Perhaps a very small subset of users hitting your application, but you want to make sure that the responses can come back very, very quickly. The one time I've used this in my sort of consulting days was when building a dashboard for a maximum of sort of 10 users on an internet application. And it helped to reduce the response time from 20 odd seconds down to single digits because I was calling out to lots of synchronous APIs. The last one is long-running event-driven. So this is where a request comes in and then we kind of want to put it to sleep until some other event somewhere else takes place. And then once that event takes place, the request needs to wake up again and then send data back down to the waiting client. It's typically used in long polling or HTTP streaming. In long polling, obviously, it's going to go to sleep, and then when there's data available, the request will return with the data that came up. In the HTTP streaming scenarios, the request will actually go through a series of, I'm asleep now, oh, there's data, send that back, now go back to sleep, oh, there's data again, and send that back again. Canonical example of this in the .NET world is in WebSockets, which we'll see a demo of in just a moment, and of course Signaler, which is the abstraction layer on top of WebSockets and other HTTP streaming mechanisms that kind of do this for you. So let's get into some demos. Yeah. I think I'm up first. Oh, let's go back.
I think you are.
All right. So let's jump over to VS and find the one that has my code in it. Let's have a look. So here's mine. I'm going to start up my solution here. So So in ASP.NET 4.5, we've added a whole bunch of new asynchrony points such that you can exploit those when doing asynchronous programming. So I essentially have an empty web application here. I'm going to go ahead and add a new generic handler. So let's go into my templates. I'm going to search for handler because there's a lot of items in here now. It's easier for search. There it is. And we're going to call this thing download the web.ashx. And we'll see we get a nice useful item template here that's allowing me to create an HTTP handler. And what I'm going to do now is delete everything here and also delete what I'm deriving from. So some of you may have built HTTP handlers before. You may have even used the async version of that HTTP async handler. But if I go ahead and implement that, what you'll see is I get a lot of code that looks like APM. That's stuff that we introduced in .NET 1.1. I have a begin process request and an end process request. It's not very modern. Well, I'm glad to say that we have a new base type that you can inherit from called HTTP task async handler in ASP.NET 4.5. And what we'll see is that the one thing I have to implement now is a task returning version of process request async. Let's just clean up some of this template code here. So what I want this request to do is download HTML from another website and then return it to the user. So let's go ahead and do that. I'm going to go ahead and say using, let's have a look, HTTP client. So I'm going to say client equals new HTTP client. So HTTP client is a new type in .NET 4.5. It's the one that has the mirrored API with Web API, which we'll have a look at in a little bit. And so now I want to go ahead and download something. So I'm going to say var Twitter, let's go and download Twitter, equals await. This is my async keyword coming in. Client.getString async. So I want to download a string from this server, http:// twitter.com. And at the moment, my await isn't showing up as blue because I haven't marked this task, this method, as async. So let's go ahead and do that. So I put the async keyword in front of the type that I'm returning from this method. And now you'll see that the await is actually blue. And if I hover over the var here, we'll see that the type of that is string. Because the method is getString async, it actually returns a task of string, which you can just see there on the right-hand side. And so if I put await in front of that, I'm going to get a string out as a response. Now I'm going to go ahead and write that out to the response. So context.response.write Twitter. I'm going to build that. Everything's good. Let's run this up in Chrome. So from here, I'm going to go to download the web. And you can see I've got Twitter. So I've actually just taken the HTML directly from Twitter. I've pasted it, essentially taken it and then returned it to this client. And now the browser is doing all the rest of the work of pulling all the other resources and images and things come down. OK, so that's fine. I'm doing one thing asynchronously. What about if I want to go ahead and do something else? So let's go ahead now and download Bing. So let's do the same thing. In fact, let's just copy and paste this to save time. And I'm going to go ahead and download bing.com this time. And then I'm going to go ahead and write Bing out to the client. OK, so that looks straightforward enough. Let's come back and hit F5. And what do we see this time? OK, I get Twitter, and then I get Bing on top, because I've now got two lots of HTML in the same page. But you can obviously understand what's going on here. It's kind of easy to follow. All right, but at the moment, I'm doing things sequentially. Brad mentioned before that async await allows us to write sequential code that is doing asynchronous operations. In this case, I may actually want to introduce some parallelism. For instance, while I've gone off and downloaded Twitter, I'm going to start writing that to the client. But this call to write all that information to the client is blocking. It's going to sit there until it's finished writing all that HTML down to the browser, and then it's going to go off and start asynchronously calling to Bing. What about if I want to push this content down to the browser while at the same time firing off the next request to Bing? So let's go ahead and do that. So I'm going to call write to buffer that into the response stream, and then I'm going to asynchronously flush that information down to the client. So let's call async, we'll do this as a flush task, and this is context.response.flush. Now, we see that we have a begin flush and we have an end flush available to us because we support async flush in 4.5. We don't have what we call an async flush method. I don't have a task returning method, which is a shame, but we can very easily create one. So let's do that. So let's create a task, a class down here, public static class. We'll call it HTTP response extensions. And then in this, I'm going to create myself a helper method. So public static, this one needs to return a task. And I'm going to call it async flush. I'm going to take in the HTTP response as response. And I'm going to write a very simple bit of code. I'm going to say if response.supports async flush go ahead and return task.factory.fromAsync. So this is a factory method available in the .NET framework that takes APM-style begin-end method pairs and turns them into task-returning methods. So in this case, it's going to be response.beginFlush, response.endFlush, not end, that would be bad, and then I'm going to add null for the state there. And then if I don't support async flush, all I'm going to do is just go ahead and do it synchronously, so response.flush, and then I'm going to return task.fromResult 0. So fromResult is a new method in 4.5 that lets me return a task that is already completed. It doesn't represent anything that's currently running, it's just already done. And I use fromResult 0 because I know that this task is actually cached in the CLR because fromResult 0 is kind of the default task that you're going to return. So now that I have async flush, let's come back up here. Let's call it flush async because that kind of marries with the rest of the API names. I've got my flush async up here, so now I have a task that represents this flushing down to the client. I'm going to change this to be a task, so I'm going to get rid of the await keyword in front of it. So remember before when I hovered over, we saw that var was actually a string? Now that I've removed await, you can see that var is now back to being a task, because what it's giving me is the handle that represents this asynchronous operation. So I now have two things going on at the same time. I'm flushing data down to the client, and I'm downloading more data from Bing. What I want to do now before I write the result of Bing back to the client is wait for both of those things to finish. So I'm going to say task.waitAll, and I'm going to pass in the flush task and the Bing task. And now my code is going to go to sleep, essentially, until both of these tasks are finished. So this isn't a blocking wait, this is an asynchronous wait. I'm still using the asynchrony points in ASP.NET here. And I have to put a wait in front of that. So then the last thing I can do, oh, no I don't. When all, because wait obviously does block. When all will give me a task that represents when those two things are finished. And then finally, I can go ahead and use that last Bing task that contains the result, and I can call .result on that. So .result is the property we saw in Brad's slide before that gives me the result of a task that is finished. Let me rebuild that. Let's come back, hit F5. And what we'll see is I get the same result in the client, but in the background I was using less threads while the downloads were happening, and I was able to push to the client and receive from another server at the same time. Now the last thing very quickly is that I may want to support cancelling asynchronous operations when some type of bad thing happens in the client. So in the case of ASP.NET, we have this idea of request timeout. If a request takes too long in a synchronous scenario, we'll actually thread abort the request and your code will just stop running immediately. For asynchronous requests, we don't do that. We're a little bit kinder. And in 4.5, we actually give you a primitive that you can use to pass through to async APIs that tells them to cancel if the request is timed out. So I can go to context dot request, nope, not that one, request dot timeout token. So this is a cancellation token, which is a type that's in the task parallel library introduced in 4.0 that will get tripped when this condition is met. So when the request times out, this token is going to fire, and getStringAsync is going to stop its operation and mark the task as cancelled instead of as completed with a response. So this just allows me to very quickly free up resources that are being used by asynchronous APIs immediately as soon as any type of situation like that occurs. So obviously that's going to build. I'm not going to demonstrate timeout, but that's a very quick overview of some of the new asynchrony points that we've added in ASP.NET 4.5.
All right. Thank you, Damien. Just a quick reminder, if you do have questions, please tweet them to us. Yes, this camera, thank you. Please tweet them to us, #CH9Live, or you can use the Jabber channel that we mentioned earlier. We actually received a question on Twitter earlier. This question is, in MVC4, I sometimes end up with a null HTTP context.current after using async await. What's the root cause of this? Well, the most likely root cause is here in webconfig, there's this app settings key that's present by default in the 4.5 project templates. And this app settings key basically says, hey, ASP.NET, use the new asynchronous pipeline that's more friendly with task, rather than the old one that's been in ASP.NET since 2.0 that's really optimized for the begin-end method pairs. So if you are finding that HTTP context.current is null, just make sure that this app setting switch is present. Again, if you need it, you can just make a new 4.5 project template and it will be there by default for you. So, my demo is going to be about WebSockets. WebSockets in 20 seconds. A client connects to a server and sends an HTTP request with special headers. The web server responds back HTTP 101 with special response headers. These headers combined form what's known as the WebSocket handshake, and at that point, the HTTP-ness of the request can go away, and what you're left with is a raw TCP socket in which the client and the server can do real-time bidirectional communication. So, there is a client-side component and a server-side component to WebSockets. What I have here is a simple application that just has a basic HTML page that does three things. The first thing it does is it opens up a WebSocket connection to handler.ashx, which you're going to see me right here in a minute. The second thing it does is there's a button on the page that when I click this button, it's going to take whatever text was inside of this input and it's going to send it across the open WebSocket channel to the web server. The third thing is that when the server sends data down to the client is just going to display the data directly in the page itself. So let me just show you what this page looks like real fast. Now, you'll see here what the basic skeleton is. It says socket closed right now because there's no endpoint for the page to connect to. We haven't written the endpoint yet. So let's just go ahead and do that. So what I'm going to do first is I'm going to pull down the Microsoft.WebSockets package. We actually include WebSocket support in SystemWeb itself. However, the support that it gives you is very elementary. It's basically the equivalent of a raw stream. The Microsoft.WebSockets package just provides a nice abstraction on top of that provides an event-driven interface around WebSockets. So now that I've pulled the package in, let me just go ahead and create my handler. My WebSocket handler. I'm going to implement the abstract base class that was inside of that package that I just brought down, WebSocket handler. And this, remember what I said, this exposes WebSockets via an event-driven programming model. When I say event-driven, I'm talking event-driven in the general sense, rather than the language keyword event. So to handle the message received event, I'm going to override the onMessage method. And right now, I'm just going to write a simple echo server. So whenever I receive a message from the client, I'm just going to echo that exact same message back to them. Now, I've written the WebSocket handler itself, but I haven't written the iHTTP handler that interfaces with this. So let's just go ahead and do that now too. So add handler. You'll see that ASP.NET has automatically created an HTTP handler for me. What I'm going to do is I'm going to bring in the Microsoft Web WebSockets interface because I'm going to call an extension method on HTTP context. And context accept WebSocket request, new my WebSocket handler. Let me go over what this line of code does real fast. So remember how I said that in WebSockets, you need to kind of get rid of the HTTP-ness of a request so that you can use the raw TCP stream? Well, what this accept WebSocket request method is doing is it's telling ASP.NET, finish the current handler, run the request all the way through end request, and then do the handshake on my behalf. And then once you have the raw stream, pass it to the my WebSocket handler type that I just instantiated. So let me go ahead and run this demo and see what happens. You'll see that the browser says socket open, and I can now go ahead and send data to the server, and the server is in real time going to receive the data and echo it back to me. Hello, world. Oh, I don't know why that's not working right now, but let's pretend that works. So, you know what? I'm going to use IE for this. Sorry, Damien, I know you love Chrome. There we go. There we go. Hello, world. There. So you can see that everything's working. The server's doing bidirectional communication. So, what's going on with threading here? Well, because this is event-driven, there's a channel open between the client and the server. And while the connection is idle, there are no threads currently serving the request. There's no work to do. There's nothing queued to the thread pool, so we don't do anything. The thread count basically is 0 for this application right now. However, when a request or when a message comes from the client to the server, an event is tripped, a work item gets queued to the thread pool, that work item being the onMessage handler that you just overrode, and that now executes on a thread pool thread. So now we have one thread running. All this handler is doing, remember, is echoing it back out to the client, and then this thread is now released back into the thread pool to do more work. So you can imagine that this scales magnificently. You can have hundreds, thousands, tens of thousands of connections all to the server simultaneously, and as long as most of those connections are idle, your thread count's going to be near zero. Now there is one more thing that I want to demonstrate here, and that's I'm discussing event-driven here in the context of the server needs to respond to an event coming from the client. Now, I can also say the server doesn't necessarily need to respond to a client-driven event. It can respond to, honestly, any event that it wants to. So let me just make a minor modification here. Private static read-only. So I'm going to make a new collection of WebSockets, and when this socket is opened, so override the onOpen method, what I'm going to do is I'm going to add this particular WebSocket instance to that collection that I just created. When the socket's closed, this type will automatically deregister itself from the collection. And I'm also going to make, for convenience, a broadcast method that takes a message as a parameter and broadcasts it to all listening sockets. And again, this collection type is part of the WebSockets package. This broadcast method is part of the WebSocket package. All I'm doing is making a public accessor around it. Now say that I have a stock ticker. I receive my stock ticker data from an external service, and I want to echo that data out to any listening clients. Let me just go ahead and create a global ASAX that can do this. So Brad mentioned earlier that one of the asynchronous patterns in the .NET framework is to use iObservable. Well, let me take a look at what interfaces my external stock ticker service implements. So you can see that the ticker is actually an iObservable, so it takes as a parameter an iObserver. So let me just go ahead and create an iObserver real fast. And this stock ticker is going to push down to me an asynchronous enumeration of decimal values, where each decimal value is the current price of the ticker symbol that I'm interested in. I don't care about completed and error, but whenever I receive a next decimal value, I want to take that value and I want to broadcast that value to all listening clients. So now that I've created the iObserver, all I have to do is say, subscribe the iObserver to the iObservable. Let me go ahead and recompile this. Go back to IE, refresh, and you can see that every time the server receives a stock ticker data point from the external service, it's going to push that out to all active clients. I can, for example, open up a new tab, and you can see that, you can see that, yes, it actually is broadcasting to all active listeners simultaneously. So that's, in a nutshell, how WebSockets works and how it can be used for event-driven asynchrony in ASP.NET. Brad?
Cool. So we do have a question from Tugberg. In terms of performance, what would be the things to keep in mind when doing parallel I/O operations in ASP.NET? There's a few things that come to mind. The first thing that jumps to my mind is that there are limits to how many simultaneous off-box sort of network calls you can make in .NET. When I say limits, they're configurable, but they are there by default, especially if you're making those calls to the same server or at least to the same host name. I think by default it's 2 from the same process to the same server, and so you'll have to go in and adjust those limits. Beyond that, guys, do you have any other thoughts on what other performance things to keep in mind when doing parallel I/O operations in ASP.NET?
Well, so I can say that the demo that I'm going to do after your demo, I'm going to show some of this.
Perfect.
So hang on to that question for another 10 minutes.
Fantastic. Okay, so I'm going to go back over here. I'm going to tortoise again. I'm just going to fast forward my demo a bit. to this point right here. Okay, so that said success, so that's good. Beautiful. So I'm going to show you how we have asynchronous APIs in web forms for doing things like asynchronous data binding. So I have a customers page here. Let's find my web async data bind. Here it is. So here it is it's just a list view. I'm using the new strongly typed data binding features in 4.5. So I have an item type set to async.customer. My project's called async. I have a customer class, which is very boring. It just has an ID and a first name and a last name. And then I just am building an HTML table based on that information. If I go into the code behind of this file, we can see that at the moment, I'm not doing anything particularly asynchronous. In fact, at the moment, this is completely synchronous. This is showing how a lot of people will be doing off-box web service calls today to some back end to then get some data and turn it in to something you can data bind. So I've newed up a web client. I'm then saying download this string. So I've actually got another handler in this project that is acting as my web service for this demonstration. And it's just returning a JSON payload, which is an array of multiple customers. So then I'm deserializing that using JSON.NET into my IEnumerable of customers, then setting my results.dataSource to that and calling data bind. So very, very typical thing that people have been doing in ASP.NET for nigh on 10 years now. So what do I have to do to turn this into something that's asynchronous? Well, we've made some changes in 4.5. That makes this a little bit easier. So first of all, I'm going to replace web client with HTTP client because I like HTTP client. I could do this with web client, but HTTP client is kind of the new hotness in terms of making calls to HTTP endpoints, so I'm going to switch over to using that. Now, it doesn't have a download string, but it does have a get string async because we saw that before. So now I have an asynchronous call off to this web service. So I'm going to say await that. Now, remember before, I'm not able to use the await keyword unless the method that I'm using it in is marked as asynchronous. But I'm in page load. So do we support async on page load? Well, we do. So I can come in here and say async void page load. And we'll talk a little bit more in just a moment about the caveats about doing this. So now I have my customers JSON. I have deserialized object. In fact, that's all the changes I have to make. If I go ahead and try and run this now, what we should see is an error. It's saying an asynchronous operation cannot be started at this time. They may only take place at certain places inside the page lifecycle. This is actually really, really useful. The other thing that we've done in 4.5, along with creating new asynchronous points, is create safeguards such that if you try and kick off asynchronous work at the wrong time in a request lifecycle, we will just Y-slob the request right there and then. We would rather introduce an error condition like this and shut down the request, then let race conditions and those type of things creep into the request. Because if you do things incorrectly, you can actually end up in a really, really bad state. For example, like deadlocking your application. So it's telling me that I can't do that right now. What I have to do is go back into my page and mark it, tell ASP.NET that this is actually an async page. I want to support these asynchronous page loads. So I go up into the page directive and I say async equals true. I'm going to come back in here now, hit F5, and there we go. I have my list view of data that I've downloaded asynchronously and then called data bind on directly. It was as simple as that to change something that was a synchronous data bind into an asynchronous data bind. Now, I did say there are some caveats in using async void. So while we do support async void, it is okay to use for very simplistic cases like this, where you're making a single async call and then you're going to do something with the result. What's going to happen is that ASP.NET, is once it exits the page load step of the page lifecycle, it's going to detect that there is outstanding asynchronous work. And the way it knows that is because the underlying synchronization context fired an event whenever asynchronous work took place. And so now ASP.NET is going to sit in a wait state asynchronously, waiting until that async work has finished. And then once that async work is finished, it's going to proceed to the next step of the page lifecycle. So ultimately what that means is that when this await call is hit, page load finishes completing the normal synchronous paths, and then after page load, it sits there and waits asynchronously until this getString async call finishes, and then it'll continue on running the rest of the code, and then the rest of the page events will happen. So that's using async void. There is another method which we actually recommend better because it actually gives ASP.NET an actual handle on the async operation rather than having to rely on the underlying sync context events to detect when async work is going on. So to do that, I don't have to have an async page load. What I need to do is go ahead and register an async task. I need to tell ASP.NET that I'm going to be doing async work. So we do that by calling register async task. This API has been there for a while now, multiple versions. I'm going to create a new page async task. Oops, and I'm going to spell it right. There we go. And there is a new overload to the constructor of this type that takes an async delegate. So a task returning delegate, that is. So I'm going to say async, doesn't take any parameters. And then I'm going to wrap this entire thing with that call. Okay, so now what I've done is I've delayed the execution of this code until later in the page lifecycle. Because for async tasks, even though this code is set up in page load, all I've actually done is tell ASP.NET to run this page async task, which is represented by this delegate when it thinks it's appropriate. And when the point in the lifecycle when we'll do that is at pre-render complete. So once you get through normal page processing, synchronous page processing, we check to see if there's any page async tasks registered. And if there are, we'll fire them off. And you can even set them off to fire in parallel if you register more than one. So now that I have this async delegate in here, registered via page async task, as I said, all the page events are going to run up until pre-render complete. Then it's going to do this async work, and then my data bind method is going to be called. So in this case, the simple case, the result is the same. But if I'm orchestrating multiple async operations, we recommend to use the page async task version rather than the async page handler version instead. Okay, so that's web forms. I think Brad's going to come up and show something else.
Okay. So the demo that I'm going to do is around Web API. So what I have here is I have a Web API project, which is actually a self-host project. One of the cool new things about Web API is that you don't have to host it inside of ASP.NET if you don't want to. So what I did to make this project is I started with File, New, Console Application. And then I came in here and I said, Manage NuGet Packages. And the package that I installed, it doesn't have package list, but the package I installed was the one called self-host. So if we do a quick search for this, we'll see the Microsoft ASP.NET Web API self-host. So when you install this package, what it does is it'll install basically all of Web API, including the libraries that are necessary to do self-hosting, which means hosting outside of ASP.NET. So this is a standard console app, so I just went ahead and do static void main, just like a regular console app. What I'm going to do is I new up a self-host configuration. I tell it to listen to localhost port 8181. And then I add, well, it looks like, this is strange. I appear to be the wrong version of this project. Let me reopen this. Okay. Let me reset this. I swear I did this. Why am I on master? I blame Damien.
Blame me.
Totally blame Damien. All right. Let me get back to step one. Where's checkout? Checkout to this. Yes. I didn't want to make a new branch, but that's okay. Better? Reload this. Okay. So what I've done is I've made a new self-host configuration for localhost 8081. I've added a logging handler, which I'm going to show you in a minute. That's going to be our first example of async code in Web API. And then I went up and went ahead and set up my routes. So if you're familiar with MVC, this is sort of the standard route mapping code for Web API. Looks very much like MVC. Start a self-host server and run it and wait for it to start running. And then basically start listening and wait for me to hit a key in order to close the connection down. So this logging handler is going to be our first example of async code in Web API. So I've derived from delegating handler. Delegating handler is part of system.net.htp, and it's sort of the pipeline in Web API. So where you might have thought about using an IHTTP module in ASP.NET or an ISAPI filter in IIS, you would consider using a delegating handler. So it's a very low-level construct. Sees all the requests as they come by, has an opportunity to perhaps intercept the request and return something different back. But for the most part, you're generally going to use these to pass data through to the underlying request. So what I've done here is the method you overload is this method called sendAsync. And you get the request in question and the cancellation token for that request. And so what I'm going to do is before I send that request off, I'm going to just log it to the console saying, here's my request. Here's the time that I started it. Then I'm going to go ahead and await the result of calling base. So what delegating handler is designed to do is take another handler, which is the next person in line to call. Okay, so he's going to say, call whoever's next, get their response back. And I'm just going to log out to the console and say, here's your response, and return it back. And then finally, what I did for controllers is I made a very simple controller. This controller is using a random number service, and it's going to get a list of random numbers. Okay, this is another example of async programming in Web API. So I've made an action, and I've marked it as async, so now I'm returning task of IEnumerable of int. And you can see here, this random number service obviously is generating really good random numbers. That's why it takes a while. And it returns a task of int. All right, so I await that, and that's going to return an int. And then I just put that in my list of results and return the results back. So what we'll see if we run this is that probably not running as admin. Okay. Whoops, that's not going to help if I don't start it as admin. Okay. So the self-host server requires us to run as admin because obviously we're opening a random port in a box. Thank you for security. I just opened the wrong project. I don't see my project. Let me go grab my project. Okay, let's go ahead and run this now. And you can see we're now listening on localhost port 8181. And let's go grab a browser. And we will do localhost 8181 API random. We'll get back 5 random numbers by default because that's what our controller did. And you can see this random number service takes a while, right? It took about 5 seconds for that request to come back. So if we look at our log, we can see, yep, the log shows us here that we did take about 5 seconds for that to come back. Where'd my command prompt go? Oh, I hit a key. I made it go away. It's a little too aggressive in disappearing. So you can see that what we've done now is we've waited 5 seconds. But the great part about having it take 5 seconds is because we went async all the way through the pipeline, so that we didn't actually lock the thread up for very long. Because at each step in a pipeline, by using the await keyword, we're basically saying something here is taking a while. You can have the thread back to process more requests. And then when our data comes back, then we'll get another thread out of the thread pool and finish the request. So we have a question from Philip, says, does async void ever make sense in any scenario? Wouldn't that just be fire and forget? That's a good question. So async void is kind of a fire and forget, right? You don't have a task. You don't have anything you can look at. Async void is actually pretty dangerous. I tend to think that the reason that async void was put into the language is basically for events. So if you think about the event subscription model in .NET, you're usually, in result of an event, the event handler has to return void. So if you want to do asynchronous work as a result of getting an event in .NET, you probably have to have an async void method to do that. Now, bearing in mind, that can be dangerous. So like in a user interface case where the application is always there, it's not so bad because async and await will put you back on the UI thread. But like in the case of ASP.NET, where your request might have disappeared out from underneath you, it can be pretty bad. That's why the guys went to all this trouble in ASP.NET to actually make sure that async void was detected, and you got a warning about it. And it's supported in a few very select scenarios, but for the most part, unless you're subscribing to an event and you're in a long-running UI application, you probably shouldn't use async void. Okay, back to the sample. So the code here takes 5 seconds, right? We've now been told by by a business person, well, 5 seconds is a long time for a request, 10 seconds, 30 seconds. We don't want people to have to wait, right? If the server is busy, we want them to get a busy notification. So what we're going to do is go ahead and pop Solution Explorer back up. We're going to add another handler. We're going to call this a timeout handler. Okay. And once again, we will derive from delegating handler. Okay. And we're going to override send async. This time what we're going to do is we're going to take and create a scenario where we're going to pass through a cancellation token that automatically cancels a request after an amount of time has passed. So let's go ahead and use cancellation token source. Cancellation token source. 2 Ls. So this is in system threading. One of the constructor overloads for cancellation token source takes a timeout. Okay, so this is how long do you want this token to last before it gets automatically canceled in the timeout. So let's say 2 seconds. And now what we're going to do is we want, we're clearly going to want to call up to the base service. But we want to pass our own token along here. We don't want to pass the original token we were given. And just as importantly, what we want to do is we want to take and wrap this in a try catch. And we want to catch task canceled exception. I want to say if the task got canceled, then what I'm going to return back is an error response with a status code of service unavailable. That's 503. And we'll go ahead and we'll put that exception in there. So after we've done this, we need to return this. So in a successful case, we'll get back a response. In an unsuccessful case, we'll get back an error response. The last thing we need to do is we need to put this in our handler list. All right. And we'll build and we'll run. So now this time when I grab my browser and I make this request, I should get a cancellation notice because this obviously takes 5 seconds, which is too long. But, okay, so I got the error back, but it still took 5 seconds. Well, that's kind of interesting, right? It took 5 seconds. Why did it take 5 seconds? Well, the reality is that nobody's actually listening to that cancellation notice, right? We gave the cancellation token to the next guy, but the controller, where all the work is being done, isn't actually using the cancellation token. So how do I do that? Well, through the magic of model binding, we can take in cancellation token as a parameter. Now we can periodically check that token to see when the cancellation has been requested. So we could say, for example, after every await, we will say if token dot is cancellation requested, and just go ahead and return whatever we have done up to this point. So this is me now checking the token periodically, knowing that this thing is going to take a little bit of time. Every time we go through the loop, we're going to check the token automatically. So now if we run this, what we should see when we request it with the browser is that we get a cancellation notice back much quicker, right? So this time it only took, well, a little bit over 2 seconds, right? So once the token had triggered, then we can automatically see what's going on here. But we did something bad, right? The bad thing that we did was we took this cancellation token and we didn't actually pass the cancellation token through that we were given. So this cancellation token here that's given to the handler could be coming from the host, and so that cancellation token could represent any kind of cancellation reason, like the client disappeared or the network disappeared or anything like that. And so we do want to pass that through. So I can't pass 2 tokens, but what I can do is I can use the cancellation token source, and I can create a linked token source. And what linked token source lets me do is pass any number of cancellation tokens together, and it merges them all together into one cancellation token. And what it gives me back is a new cancellation token source. So I want to pass this token and the cancellation token that I had been given before. And now I want to pass the merged token through. So this is actually the more correct way to do this. So now I'm not only taking the cancellation token I was given, I'm adding new cancellation behavior as well. So a question. Philip asks, will the source code for these demos be available for download? Yes, they will. We'll give you the URLs at the end of the presentation. OK. So that is now the correct version of how to do this. So we now have the final bit here, which is we're taking 5 seconds, but we really don't need to take 5 seconds, right? Because our random numbers are, well, they're not, I can run them all in parallel. They're not related to one another. So what I'm going to do, and this is ties into the question from before about parallelizing asynchronous I/O. So the other thing I'm going to do is I'm going to go ahead and if I didn't do this already, because I don't remember if I did it, I'm just going to pass the cancellation token to the random number service, which you can see our very expensive random number service here is an await task delay. So we'll do cancellation token. And task delay, nicely enough, takes a token, so we can just pass it through the task delay. So now if I go back here to my controller, you can see I have this loop here where I'm doing a wait for each number to come back. And so I wait for each number to come back before I get the next number. Well, an easy way to do this is to just run this all in parallel. So instead of keeping a list of ints, I'm going to keep a list of task events. Right? And now what I'm going to do is call and basically start all the services running in parallel. But what's great about this is we talked about, this might be expensive. It's going to take a lot of threads. So in this case, it'll take 5 threads. But those threads will immediately go back to the pool. Why? Because everything I'm doing is using async. So what's nice here is I'm not actually consuming that thread for very long. So it'll spin it up, give it back, spin it up, give it back. And the second that it has to wait, it's not actually spending in the thread. But now here down at the end, I have a list of task event, not a list of int. And I obviously need a list of int back. So I'm going to use the magic of link. And I will need a link namespace for this. So I'm going to use the select method in link, which is a projection. So for each task, I'm going to return the result of that task. And so now the result of that is a list from the list of task event is an enumerable event, exactly what we wanted. OK. However, we don't know that we have results yet, right? We can't call result until we know that things are done. So we're going to use the same technique that Damien used. And we're going to do a wait task when all against our results. So wait for all the results to finish, and then we can return them back. So now, one last time, bring this up in my browser, hit F5, and we should see that we should get an answer back in 1 second because all 5 of them ran in parallel. So now it took 1 second. Okay? So that is our demos for today. You guys want to come join me back on stage?
Be glad to.
All right. So the final thing we want to talk about is anti-patterns in server async. Just a reminder, if you have questions, hashtag #CH9Live. There's clearly going to be a lot of stuff in async that's dangerous. We've already talked about some of it, right? So let's make sure to highlight for everybody the things that can be dangerous when you're writing async code on your server. All right, Levi?
So remember my diagram from earlier. The work items that are being used to process requests are just being dispatched straight to the CLR thread pool. Similarly, whenever you use threadpool.queueUser work item or task.factory.startNew, you're queuing work items to that exact same CLR thread pool. There's only one CLR thread pool for the entire application. Now, this means that if you're attempting to queue up a work item on a background thread because you don't want to tie up the original thread, in UI programming, this might be beneficial, but in a server, remember, there's no UI. Each thread is basically as equivalent as the next, and the end result is that you're not actually going to be freeing up any resources for ASP.NET. In fact, you're going to be consuming more resources because there's going to be a period of time where you now have 2 threads instead of 1 doing the same amount of work.
And there's an interesting caveat here about servers and clients, right?
Yeah.
If you're writing a library as opposed to an application, and your library code might be used in a server or a client, sometimes you just have to bite the bullet and run on a background thread because you don't know whether there's UI available or not.
Yeah.
So a good example of this, formatters in Web API. You can use formatters on the server side, but you can also use formatters on the client side to make requests. So.
And just the line at the end there, yeah. So if you're writing something like a message handler, like we saw Brad do before, and the work you're doing is actually synchronous, but you're part of an async pipeline, which of course Web API is, then you can use task.fromResult in 4.5 or task completion source in 4 and above to return a task even though you didn't do any async work.
Right.
You shouldn't be just calling task.factory.startNew because you have to return a task. You really should only be doing that if you understand that you're going to be creating a background thread. So use those two other types to return tasks when you can't actually create a task.
Right. Task completion source of T is also useful if you need to return something which isn't a result, like if a faulted or a canceled task.
Right.
You can use task completion source of T to do that. So next one, ASP.NET intrinsics and worker threads. So this one came up earlier in one of the questions, and Levi highlighted this, which is don't use ASP.NET intrinsics if you don't know what thread you're on.
Yep.
And the best way to know what thread you're on is if HTTP_context.current is null, you ain't on the right thread.
Right.
Right. So in 4.5, the easiest way to do this is async and wait. 4.0 synchronization context post. So talk about some of the, you've obviously been witness to some of the debugging fun that happens here.
So what can go wrong? As was pointed out in Twitter earlier, HTTP context.current can be null, which if you happen to be using this on a thread pool thread and you hit a null reference exception, well, an unhandled exception on a thread pool thread crashes the application.
Now,
you might not think that this is a good thing, but I actually consider that to be the best case scenario. In the worst case scenario, and by worst case I mean you're going to have an interesting time trying to debug this, you might have things like, oh, I meant to write to this HTTP response, but my response actually got sent to a client other than who it was intended to go to.
that's pretty evil.
That's pretty bad. Remember, we sit on top of IIS, and we have to pool a bunch of our resources, such as memory queues. So if you're writing to a memory queue that's been repurposed for another request, and you're not using synchronization context.post, we might not have detected that switch took place, and all hell just breaks loose.
The other thing is interesting, we keep saying use async and await in order to make sure it does the right thing. That only works if you call await on the request thread to begin with.
Yes.
That's true.
Because the sync contexts that get, basically async and await are going to capture the sync context for you and then ensure that any work that's done after the async work is finished comes back via sync context.post. But if you have some random background thread and then you call async await, there's no synchronization context there, so you're not going to get any benefit. So you really have to be aware of what thread you're on before you even start dispatching asynchronous work.
Absolutely. Issues with wait and result. I have a blog post series that I have yet to finish, but about task parallel library. Wait and result can be very dangerous, as Damien almost learned in this demo.
Yes.
Right. So calling wait obviously blocks. Right. And the whole point of this stuff with async is don't block. But the insidious one that I mentioned just a couple minutes ago is calling result on a task that's not finished also blocks, which is why I had to put that await task when all to make sure that we waited asynchronously instead of blocking the thread. So obviously async and await is going to become a pattern here.
Some of the bad things that might happen if you do this at the wrong place, and even though in 4.5 I showed you we've tried to put in safeguards so that we abort the request if we detect nefarious async behavior, you can still deadlock your application by doing something as innocuous as calling .wait or .result in the wrong place. Because those things, especially if you're on the request thread and that sync context thing is happening, ASP.NET does locking on these things to ensure that the intrinsics are set up correctly, and if you do this at the wrong place, you can deadlock your app.
Yes, because you'll be blocking the request thread, nobody else can get back to it.
Right.
I'll call synchronization context.post and never get the message.
Never get back, so.
That'd be bad. Similar to this, issues with continue with. So async and await are sort of the way you would do this in 4.5, but the continuation that I showed with continue with in my early slides is how you would add behavior onto the end of a task when it's done, regardless of what state it came through. But continue with is ignorant of the sync context, right? So the async and the await machinery that get written by the compiler are going to automatically make sure you're on the right sync context. So if you don't have 4.5, you have to capture the sync context ahead of time and put yourself back onto it with post. And of course, the second one is kind of an interesting one. I mean, the compiler sort of does some magic for you to try and keep you on the same thread as much as possible.
Yeah, so in the .NET framework, thread hops they're not terribly expensive, but they're also not free. the async and await keywords are actually specially optimized such that they'll try to keep you on the same thread if they can. And the continue with method, if you just call it, is by default just going to push you off to a random thread pool thread. That thread hop will hurt performance if you're doing too many of them in your application.
And it's a really interesting point because we keep talking about how async is fantastic because it can improve the throughput and the performance of your application. The thing you need to remember is that in the desktop app, you can create literally hundreds and thousands of threads and you probably wouldn't see any detriment. If you're doing this in a server application where you're serving hundreds or thousands of requests and then they're doing maybe hundreds and thousands of threads, you're going to see your performance absolutely tank. So you have to be really, really careful and aware of when these thread hops are taking place if you have high load. So.
Yeah, I mean, the first thing to even think about, right, is that every thread has a megabyte of stack. So if you had 1,000 times 1,000, you have 1,000,000 threads. For some reason, you have a gig of stack.
Yeah, well, an interesting point, actually. In ASP.NET, by default, we actually only have a 1/4 meg of stack per thread, but still, that's a lot of memory just for threads.
That's still a 1/4 of a gig.
Yeah, but again, if you're using the right intrinsics and the right APIs, the threads will all be managed for you. You should never have to actually manually create a thread at all.
Exactly. Thread local storage, this is kind of a nasty one, right? So the idea here is that your request, Levi said, requests have a thread affinity, but that's both right and wrong. I mean, they have an affinity to the thread they're currently on, but they can hop threads. But any request only belongs to a single thread at a given time. But every asynchronous operation could mean you come back on a different thread with the request associated with it. So if you do things like thread static, then that data is not going to be there. So
the other thing to remember is that your code isn't the only code running in a request in ASP.NET. I mean, there is a full pipeline. There are many modules installed, and those modules run at particular events. You might have third-party modules, and they can be asynchronous. And so they may be doing things that force you to hop a thread, and you didn't realize, even though your code is synchronous.
Right.
So you can't even just say, oh, my code is synchronous, therefore I'm never going to hop a thread. We may swap the thread out underneath you without you never knowing.
Right.
So you need to be very, very careful about where you store state, which
Absolutely.
is the last point here.
Right.
Use HTTP context items.
Yep. So in summary, these are some of the big ones, right? Levi, you came up with this list.
Yeah, so we keep harping on this point, but it's a very important point. If you're calling threadpool.queuser_work_item or task.factory.startNew just to hop threads in ASP.NET, you're not actually going to see a performance gain. Remember, all you're doing is consuming a resource that ASP.NET could have consumed had you not called those methods.
Right. So all these things, thread, queuser_work_item, task run, task factory start new, these guys all basically spin up a new thread out of the ASP.NET thread pool, right? Because it's all just one thread pool. And of course, one more thing, right? Async and await.
Use 4.5.
You should. That should be the title of this talk. Use async and await. Use 4.5. I mean, it makes it so much easier. You get to write this nice code that looks sequential, looks like it could be synchronous, except little await keywords peppered in. You don't even have to think about it. So. So people are asking about code. Here's demo code. We have a question.
Yeah, so can a self-hosted HTTP listening app use any of the IIS features like failover and load balancing, or is IIS hosting required? So load balancing, so in IIS, load balancing can be achieved in a number of ways. You can use ARR if you have a front server, application request routing, and then have that load balance out to multiple servers. Or you can just use standard Windows load balancing services, in which case IIS isn't involved at all. You can certainly have multiple servers running self-host, and then have Windows load balancing server do the peer-to-peer negotiation about which request will be handled by which server, because that's actually TCP level load balancing rather than this. Failover, IIS has really nice process management and error detection and restarting of app pools when things happen. That's IIS. That's nothing to do with self-host, unfortunately. So if you want that type of logic, you'll either need another process that sits there and launches your app and then monitors, or another process that sits there and monitors your app and kills it and sets it up yourself. So.
And to be clear, the self-host library that we ship for Web API is written on top of a very light WCF layer on top of HTTP sys. You could write it on top of anything you want. In fact, Louis Desjardins, one of the developers on ASP.NET, has a project where he has basically a direct link into IIS, right? That you can spin up a CLR thread pool. So it's kind of like ASP.NET, but doesn't have the ASP.NET pipeline. So you could theoretically, host this as your self-host for Web API, because the hosting layer in Web API is pluggable.
Right.
Right. So in that case, you could take as much advantage of IIS as you wanted to, because then you really do have IIS available to you.
And an example of that is the node for IIS, for instance, where
Right.
they've done exactly that. They have a native
Exactly.
IIS module, so they get all the benefits of IIS process management, but there's no ASP.NET involved at all.
Right.
So,
And so, the answer as to whether or not you'd use a self-host or a web host is, do you want to have ASP.NET Classic, MVC, web forms, web pages code running alongside your web API, or does your web API, is it pretty much standalone? That's kind of like your first decision point. So it looks like we've probably answered all the questions. Again, we want to thank you for tuning in today or streaming us later if you're streaming us later. Questions were great. I hope you guys have a terrific conference. Lots of great topics going on both today and tomorrow. And two of the three of us will see you in a few hours.
great, thank you.
Yeah.
Thank
Thank
you.
you.